Okay, let's start recording. Okay. Okay, let's start. Okay, let me just slides. Okay, for this week, I will do concerning chapter about matrices. So continuation from last week about vectors. Okay, so this matrix part, I think will be most important for your GNC class, guidance, navigation, and control, because that class, that course, I think Wong Junta, you are taking that course this semester, right? GNC.
Yes, correct, doctor.
So you have started okay, so that course use a lot of mathematics stuff, especially concerning this matrix, and later on you will see some calculation on eigenvalues, eigenvectors, etc. Okay, so this is I just explaining to you guys the application of this topic. Okay. Okay, so good morning, Wakas. Welcome. You were just going to start. Okay, so I've just uploaded these slides and another slide concerning tutorial on Putra Blast. So you can download the slide and you can look at the tutorials examples that I've uploaded later on. Okay, so first, matrix, some basic definitions. You already know about this. So a matrix is a rectangular pattern or array of numbers. So it's like vectors last week. Okay, for example, you have A 3 times 3. This one is 3 times 3, 3 times 3 matrix, and this one is 2 times 3 matrix, and C is 1 times 3. So basically, we will read the row first. So how many rows, and then we read the column. So 3 times 3, 2 times 3, and 1 times 3 vectors. Matrix, sorry. So means that vectors also, okay, from last week, vectors also, we can write the vectors in terms of matrix, if you remember. Okay, so if you have usually the vectors 2, 3, 4, okay, in 3 axis, X, Y, Z. So you can write the vectors in terms of in matrix form also. Okay, next. Okay, some rules concerning the matrix, addition, subtraction, and multiplication. Okay, so if you have the A and B matrix, the 2 times 3 and also 2 times 3. Okay, so we can find A plus B and A minus B. So basically, for addition and subtraction rule, tambah tolak, addition and subtraction rule, the rules is the size of the matrix must be the same. So A and B must have the same size, 2 times 3 here, in order for the addition or subtraction to be valid. Okay, otherwise we cannot, if they don't have the same size, we cannot add addition and subtract both of the matrices. Okay, so basically we just for example, A plus B. So we have 1 here and 1 here. So 1 plus 1 equals to 2, 5 plus 2 equals to 7, etc., etc. So each component, we add them or subtract them. Okay. So the matrix addition is commutative or associative. Okay, and then multiplication. Okay, so for example, okay, for the product, the rules is a bit different. For multiplication, it's a bit different. So example, we have A 1 times 2 and B 2 times 3. Okay, the size of the matrix. So if we look at the, for example here, okay, 1 times 2 and 2 times 3. Okay, so if the number of the column for matrix A is the same as the number of row for matrix B, so we can multiply and form the product of AB. Okay. So we look at the number of the column of matrix A and number of the row of the matrix B. Okay, if they are the same number, for example here 2, A have 2 columns and B have 2 rows. So so both of them can be multiplied and produce the product. Okay. Okay. So for example here, example B 8.8. Okay. The B 1, 2, 3, 4, 5, 6 and C 1, 2, 4. Okay. So B has order of 2 times 3 and C has order of 3 times 1. Okay. So 3 and 3, 3 columns for matrix B and 3 rows for matrix C. So we can form the product. The product exists. Otherwise, we cannot multiply. Okay. And we have order. So the answer of product B and C will be 2 times 1. Okay. So the size of the product after multiplication will be this one. Okay. Maybe I use a different color. Okay. So the size of the product of the matrix will be the number of row for matrix A just now and number of column for matrix B. Okay, so for example, the example 8.8 below, B and C. So you have 2 times 3 matrix and 3 times 1 matrix. Okay, anything, I mean. Okay. So you have 2 times 3 matrix and 3 times 1 matrix. So the answer, the product of the BC will be 2 times 1. 2 times 1. Okay. Okay, so we know directly the size of the product. Okay, so from the size of the product that we expected, so we can write, okay, for example, like this, BC. So this is B, this is C. So to calculate the answer, we know that the answer of the product will be 2 times 1, like this one. So we know the first one, we are going to calculate the first row. Okay, first row and first column. Okay, so the answer 17 is from the first column because 17, the position of the component 17 is in the first column and first row. So we do first column, first row. So 1 times 1, 2 times 1 times 1, 2 times 2, 3 times 4. So we get 17. And the second one, 38, is second row and first column. So 4 times, so second row, first column again. So 4 times 1, 5 times 2, and 6 times 4. So that's how we get the product of the matrix BC. Okay, in general, the rules for the product, the multiplication, AB and BA is not commutative. Means that if we change the position of the matrix AB and BA, the answer will be different. Okay, the product form will be different. Okay. Okay, some special matrix. Okay, some definition for matrix. We have what we call as identity matrix. Okay, so identity matrix, what is identity matrix? It is a square matrix. Square means 2 times 2 or 3 times 3 matrix or etc. etc. 4 times 4 means n times n matrix mean n row and n column, or what we call as square matrix. Okay, so identity matrix is the square matrix, okay, having only value 1 on the leading diagonal here. Okay, so this is what we call as identity matrix. So if matrix identity here, identity matrix multiply with matrix A will be equal to still A. Okay, if A is a square matrix, then IA is equal to AI and is equal to A. Okay, it's something like you do 5 times 1 equals to 5. It's as if the 1 doesn't exist. Okay, so 1 is what we call identity for multiplication, the simple multiplication like this. Okay, for example, or else 5 plus 0 equals to 5. So 0 is the identity for addition. Okay, so that is the definition. 0 is identity for addition. 1 is identity for multiplication. And I, the matrix I here, is the identity matrix for matrix. Okay. Okay. We are going to need this I later on where we apply the calculation of the matrix. Okay, second one is the transpose of a matrix. Okay, we call it as a transpose of matrix A, or written as AT, like this, transpose of matrix. By interchanging, we interchange the rows, the values, the component, okay, the each value in the row and column of matrix A. Okay, for example, here, we have A, matrix A here, this one. 1, negative 1, 2, 4. So if we want to find the transpose of A, so we switch the row and columns. So here 1 and 2 is in the first column. So for transpose A, for the matrix transpose A, 1, 2 will be the row. Okay, so the same as negative 1 and 4. Negative 1 and 4 is the second row. So for transpose of A, it will become the second, negative 1 and 4 is the second column. So for transpose of A, negative 1 and 4 will become the second row. Okay, so we just change the rows and columns of the matrix. Okay. And then what else? Okay, the inverse of the matrix. Okay, how to find the inverse? Okay, for example, if for normal number, for normal real numbers, for example, if we have 5, so the inverse of 5 is 1 over 5. But how are we going to do this for matrix? Okay, so if A is a square matrix and we can find another matrix B with the property that, okay, so the inverse matrix of A here is written as B. Okay, the rules is that the inverse matrix, if we multiply the initial matrix with its inverse, will become identity. Logic, okay. For example, the number 5 here. So 5 is like the matrix A. 5 is the real number. And the inverse of 5 is 1 over 5. So if you multiply 5 with 1 over 5, you will get 1, which is 1 is the identity for multiplication rule just now, right? So means that if you multiply the matrix with its inverse, you will get back the identity. Okay, so then B is said to be if the rules is correct, so so we can say that B is the inverse of A and it's written as A with -1. Okay, we write the inverse of a matrix with the notation like that. Okay. So A minus 1 equals to A minus 1, A equals to identity. Okay, so how are we going to find what is the rules? Okay, I mean the steps of calculation to find the inverse of a matrix. So for example, matrix 2 times 2, okay, matrix 2 times 2, a simple formula exists. So for we have A, B, C, D. So the formula for matrix to find the inverse of the matrix A is, okay, 1 over AD minus BC. Okay, it's like what how we calculate the product last week. Okay, so A B C D. A B A D, sorry, A D, A times D, D donkey, okay, minus C B. Okay, so that is the rules. And then multiply with the another square matrix. We change the position of D and A, and the B and C stay at the same location, but we put negative. Okay, so this is the rules. You don't have any other choice than other than to remember the rules. Okay, the rules to calculate the inverse of matrix. So this is the formula. So you have to remember the formula. Okay. Okay, and then okay, so example. If A is 3512, find A the inverse of the matrix A. Okay, so one of the rules to find the inverse of the matrix, we have to make sure that AD minus BC, if we multiply the AD 3 times 2 minus 1 times 5 KBC, make sure that we don't get the answer AD minus BC 0. Otherwise, this will be infinity, right? If you get AD minus BC 0, then we cannot find the inverse of the matrix A. So means that the inverse of the matrix does not exist. Okay, so we must check first the AD minus BC. Okay, so AD minus BC here is equals to 1. So we get, okay, by using the formula just now. So we get A 1 over 1, okay, 2 minus 5, 1 is 1, 3. So we get the inverse of the matrix. Okay. Okay, next. Okay, next is determinants. Wait, can I macam excuse kejap 1-2 minutes nak fix a technical problem sikit. I want to fix a bit slight technical problems, okay? Sekejap 1-2 minutes.
Yeah. Mana satu cik minat? Ni. Ada satu je kan cik minat?
Wait, I want to fix the mic setting je. It's okay, okay. Sekejap. Di sini je lah. Okay, kejap. Can you see my screen matrix?
Yes, we can see that.
Okay, you can see. Okay, I just change to this desktop. Okay, so I continue. Okay, determinants. Okay, next after inverse, after we have see the how to calculate the inverse matrix. Okay, so now the determinants. Okay, so if a matrix of for 3 times 3 matrix, okay, so the value of its determinant, the matrix A, is given by okay, so the rules here, okay, so the determinant of A, we write it as absolute value like this. Okay, so we have okay, so the rules like last week I mentioned. So for example, the first one, A11, okay, so we just slash the first row and the first column. Okay, so we only focus on this square matrix A22, A23, A33, A32, and A33. So we have here, and then minus A12. So we just close slash the first row and the second column. So only have A21, A23, 31, and 33. And final one, final component A3, A13. Okay, just close this one. So we get A21, A22, A31, A32. Okay. Okay, so example here, find the determinant of the matrix A, 1 to 1, etc. So the determinant of A is written as like this. So how to calculate it using the same formula here. Okay, so again, this one also you have to remember the steps, okay, to calculate the determinant. Okay, so you have A11 is 1, A12 is 2, negative, don't forget, negative. And then A13 is 1 again, and the rest for the matrix, the square matrix, the same as this one, the component. For example, here 3, 4, 1, 2, minus 1, 4, etc., etc. And then you calculate the determinant with the rule just now, the cross rule, cross and minus. So 3 times 2, 6, minus 4, minus 1 times 4, so we get 2. This one also, minus 1, minus 2, subtract, okay, 5 times 4. So the answer is minus 22. So the rest are the same. So that's how you get the determinants of A. Next, if A, okay, okay, this the same just now, the same example as just now, okay, just to add on the cofactor, okay, so what is cofactor? Okay, so the cofactor is the sign, positive, negative part. Okay, the positive, negative sign. The cofactor is found by imposing on the minor or a positive or negative sign depending upon its position. There is a place sign. Okay, so this is the rules just now. So that's why for the second one, A12, we need to put minus in front. So the rules is like this, plus, minus, plus. Okay, minus, plus, minus, plus, minus, plus. Okay, for each component in the matrix. Okay, so this is the cofactor, the sign for the cofactor. Okay, okay, remember vector last week, using determinants to find vector product. So we can use the concept of the determinants of matrix to find the vector products. Okay, so determinants can also be used to evaluate the vector product. Okay, so if you have the vectors A1, A2, A3, so this vector can be written in terms of vector. Okay, so it will become 3 times 1 vector. Okay, 3 row because we have a 3 component here and 1 column. The same as B for matrix B, vector B. So you can find the product. The product AB is the vector defined by this one, okay? So the rules are like last week, okay? You do the cross product, so you find the component for I, J, and K. Okay, so the rules are like I have shown you, okay? Okay, so Cramer's rule. Okay, Cramer's rules. One of the application for the determinants is using the Cramer's rule. So you have okay, these three what we call as simultaneous equations. These three simultaneous equation, or it is like linear algebra. Okay, a linear equation. This is linear equation. Okay, so we have three linear equations. So actually, these three linear equations, a simultaneous equation, can also be written in terms of matrix. So you can see here, we can regroup the component A11, A12, etc., in one matrix A, and then X, Y, Z will become a vector or a matrix X, Y, Z, and B1, B2, B3 is one matrix B. Okay. So Cramer's rule states that X, Y, Z are given by the following ratios of determinants. Okay. In order to solve these three simultaneous equations or three linear algebra equation to find the unknown X, Y, Z, one method to solve is by using Cramer's rule. Okay. So Cramer's rules is actually a method that we use to solve linear algebra, linear system, or three simultaneous equation like this. Okay. So how do we use Cramer's rule to find X? So X is equals to the determinants. So this is determinants. The notation for determinants like absolute value. Determinants of X, determinants of this matrix. Okay, so for example, X is this column, right? First column. Okay. Okay, X is the relates to the first column A1, A11, A21, A31. So we kind of like close the column. Okay. Close the column X and replace the column A11, A21, A31 here, the first column, with B, the matrix B, B1, B2, B3. So that's why we replace it here. Okay, so the rest still the same. A12, A13, A22, A23, A32, A33, still the same. Okay, we just close the column for X, the first column, and divide by the determinants of A. Okay, like how we calculate determinant just now, like this one. Okay. So the steps is quite long. Okay, the calculation is quite long. So you have determinants A. So it means that you have to first calculate the determinants A first, and then you need to calculate the determinant of each of these X, Y, the numerator of X, Y, Z here. Okay, so the same for this one for Y. Y is this in the second column. Okay, second column 2. So you just replace the component A12, A22, A32 with B1, B2, B3. Okay. And you do the same method for to calculate the determinant. So means that you have to find this determinant and also the determinant below. And the same for Z. Okay. Z is the third column, the 3, column number 3. So you have A13, A23, A23. So you just replace with B1, B2, B3. Okay. So the same thing. So by using these rules, these Cramer's rules, you are going to we are able to calculate to find the unknown XY Z. Okay, so this is one of the method to solve linear algebra. Three simultaneous equation like this. Okay, so for example here. Okay, so we have these three linear algebra, three simultaneous equation. Okay, at 3x plus 2y minus z. So we can rewrite, okay, this part on the left hand side in terms of matrix. Okay, so it will become like matrix A here. So matrix A, the determinant here, A is in the denominator here, bawah ni, below. So 3, 2 minus 1, 2 minus 1, 2, 1 minus 3 minus 4. So this is the determinants. Okay, determinants for matrix A, this part. And then remember to find X, okay? So we copy the same thing for second column and the third column, but the first column we replace with the value in the matrix B component, okay, 4, 10, and 5. So we need to do determinants for this one and also to calculate determinants of this one. How to calculate determinants? Using these rules, okay? So we get 165 over 5, 55. So the answer X is equals to 3. Okay. So the same thing, the same method we can use to calculate to find Y and Z. So Y equals to -2 using this formula and Z equals to 1 using this formula. Okay. So you find the answer X, Y, Z. Okay. The calculation is a bit long. Okay, so I don't show all of them here, but at least you know the one example to calculate X. Okay, another application. Oh, this one I missed. Okay, fine. The inverse of a 3 times 3 matrix. Okay, just now we saw the inverse of 2 times 2, right? Okay, 2 times 2. So now it's 3 times 3. Okay, so to get the inverse of 3 times 3 matrix is quite different. It's of course is longer. Okay, the steps. So to find the inverse, first you have to find the transpose of A. Remember how you find the what is transpose matrix just now by interchanging the rows and columns of A. So I go directly to the example. So for example, you have a matrix here, A here. So to first step, so there are 3 steps to get the inverse of 3 times 3 matrix. So the first step, you get the transpose of A, so means that you interchange the rows and columns. So the first column here, 1, 3 minus 1, so it will be the first row of transpose A, 1, 3 minus 1. -2, 1, 2, okay, so etc. etc. Okay, so you transpose, interchange first the row and column of matrix A, so you get the transpose of A, matrix A. Okay, next, what does it say? You replace each element of A, the transpose of A by its cofactor, by its minor together with its associated place sign. The resulting matrix is known as the adjoint of A, denoted at ADJ A. Okay, adjoint of A. Second step, we need to calculate to find the matrix adjoint A. So how to do that? Okay. Okay, this one. -7. Okay. So we need to get the minor together with the cofactor. Okay. So the first position here, 1. Okay. So it's like we slash. Okay, remember just now like we do the determinants. We close the 1, 3 minus 1 and 1 minus 2, 0. This one. Okay. Okay. So we only left with this square part. Okay. 1, 2, 5, 3. So like we do the cross product for the determinants. So 1 times 3, 3 minus 5 times 2. So 3 minus 10. 3 minus 10, so you get -7. Okay. So that is how you get the adjoint, the first component for matrix adjoint A, -7. Okay, I'll take another example. Maybe the one with negative. This one, the -14. How do you get the -14? So -14 is second row and first column. So you close this one and you close this one. Okay, so you only have with 3 minus 1, 5, 3. Sorry, I changed from iPad to desktop, so that's why I don't have I cannot write using pencil. Okay, so 3 minus 1, 5, 3. Okay, this one, this component. So 3 minus 1, 5, 3. So 3 times 3, 9, minus negative 5, minus 1, 5. So minus negative 5, so 9 plus 5. So you get 14. Okay, so the answer is 14. But the position for this position, remember the cofactor, the sign is negative. That's why we need to add on negative here. So now, this formula, okay, this cofactor display sign plus minus minus plus minus plus minus plus. So the 14 is at this location. Okay, so that's why we need to add extra negative here. Tadi? Okay, this one. Okay, so that's why we get minus 14. Okay, maybe last one. Again, we look at this minus 5. So minus 5 is the second row, third column. Okay, so second row, third column, negative sign. Okay. Okay, minus 5. Okay, so second row, third column. So you close the second row and you close the third column. You will focus on 1305. So 1 times 5 is 5 minus 0 times 3 is 0. So you get answer 5. Okay, because of the position of this component here, having the cofactor, the negative sign. So you need to add on negative in front. Okay, so once you get the adjoint of A, so you finish the second step. So finally, the inverse of A is given by the inverse of A for 3 times 3 matrix is adjoint A divided by the determinant A. Okay, so you need to find the determinant A, okay, using the rules of the determinant just now. Okay, to get the determinant A, so you get the determinant A 21. Okay, and for adjoint A just now, okay, this is the matrix of the adjoint A, this one. Okay, so you have to divide by the determinant. So 1 over 21, you divide by 21. So this is the inverse of matrix A. Okay, in order to verify your solution, you can verify by doing the identity just now. So the inverse of the matrix A multiply with the initial matrix A, you have to get back the identity, the diagonal matrices now, 1, 1, 1, and 0 everywhere. Okay, this is how you have, if you want to prove whether your answer is correct or not, your calculation is correct or not. Okay, application to the solution of simultaneous equation. Okay, so one of the application, why you need to calculate the identity, the determinant, the adjoint, inverse, etc. Okay. For example here, okay, we need to solve this. I think this is the same equation just now. It's the same example. Okay. We need to solve these 3 linear algebra equation, simultaneous equation. Okay, so you have 3x plus 2y, etc., etc. These 3 algebra equations. So these 3 linear simultaneous equation can be also written in terms of matrix form. So you have matrix A, okay, and matrix X. X is X, Y, Z, and B, the matrix B, 4, 10, and 5. Okay, so you can rewrite. Okay, you can rewrite first the linear algebra equations in terms of matrix like this. Okay, so you have A, matrix X, and matrix B. Okay, so the rules is okay, AX equals to B. So if we calculate, if we put the add on the inverse of the matrix, multiply with the inverse of the matrix here, the left and right hand side. Okay, so this part will become the identity matrix. So identity matrix multiply with X will be X because it is identity. Okay, and so X equals to this matrix. Okay, so we want to show this is we want to prove the method of calculation for the results matrix X just now, SYZ. Okay, so means that SYZ, in order to get SYZ, we need to get the inverse of the matrix A multiply with matrix B. Okay, so we must therefore first find the inverse of the matrix A. Okay, using the step previously mentioned just now. So we have A, matrix A, this one. Okay, matrix A. First step is you get the transpose of A. Okay, first step transpose of A. So just interchange the row and column, that one easy. And then you find the adjoint A. Okay, the formula just now, adjoint A with the cofactor just now, the sign plus positive negative. So you get adjoint A. Okay, the matrix adjoint A. And finally, to finish the inverse matrix, we need to calculate the determinant of A. Okay, so the determinant of A, okay, not determinant of transpose A or determinant of this one. It's the determinant of A. So, calculate the determinant of A using the formula given. So we get the determinant of A 55. Okay, so so the inverse of the matrix is the matrix adjoint here divide by the determinant 55. Okay. Okay, but we're not finished yet. Remember how to get the matrix XYZ here is by multiplying the inverse of matrix A with matrix B. So once we get the inverse of the matrix A, multiply with matrix B for 10, 5. So just multiply and we get the matrix X 3 minus 2, 1. Means that the solution is X equals to 3, Y equals to minus 2, and Z equals to 1. Okay, so this is the second method to solve linear algebra. Okay, remember just now we have Cramer's rule. Okay, this one, Cramer's rule to solve the linear algebra, the three simultaneous equation here to get the unknown SYZ. Okay, we can use Cramer's rule. Okay, so we get SYZ. So this is the first method that I showed you just now. Second method is this one. Okay, second method is by using the inverse matrix. Okay, means that you have to calculate inverse matrix first and then you get B. With B and then you get the XYZ, the vector X, the matrix X. So you get the answer, the solution for the algebra equation in the algebra 3 minus 2, 1. Okay. Next. Again, other method to solve a linear algebra means using the application for matrix is by using Gaussian elimination. Okay. This one maybe you are already familiar, but maybe you don't know the name of the method. Okay, it's called Gaussian elimination. Okay, for example, we have only two here, two linear equation, two linear algebra equation, 2x plus 3y equals to 4, 4x plus 6y equals to 7. So we can write this algebra equation in terms of matrix 2, 3, 4, 4, 6, 7. Okay, including for Gaussian elimination, we include the matrix B in the matrix. Okay, like this. So 2, 3, 4, 4, 6, 7. Okay, we write all the values. Okay, so Gaussian elimination, obviously we use the eliminate. The process is by eliminating the component. Yeah. Okay. So first, for example, okay, the first row 2, 3, 4. The first row we call it as R1. Okay, the first row 2, 3, 4. We just leave it like that. Okay, and then we look at the second row. So for Gaussian elimination, the objective, okay, the aim is to get 0 of the second row or the third row if you have 3 times 3 algebra. The objective is to get 0 for the second and the rest of the rows. Okay, so for example, this one. Okay, we try to first eliminate 4, this component. Okay, try to eliminate 4 first. So I'm going to eliminate 4. Look back at the equation. 4 can be eliminated by 4, okay, the second row, minus 2 times the first row. Yeah, 4 minus 2 times 2, 4. So we get 0. Okay, this rule. So this equation depends. Okay, how are you going to eliminate the second row? Okay, so for example, this one, because this one is 4, this one is 2. So obviously, in order to get the 4 become 0, you need to use this equation. 4 minus 2 times 2, so you get 0 here. Okay, so once you get you have eliminated the 4, the number 4 here, this first component, since it is a linear equation, okay, so you cannot just eliminate just the first number 4 here. You have to do for the rest. Okay, so means that this rule, this equation, R2 becomes R2 minus 2R1 is need to be applied for the rest of the numbers, the component in the equation, because it is still a one equation like that. Okay, so in order for the equation to be still valid, okay, means that 4x plus 6y equals to 7. So if you change one component, you have to change for the rest. So the same equation you do for the second component, 6. So 6 minus 3 times 3. Okay, yeah. 6 the second row minus 2 times 3, sorry, 2 times 3. Okay, 2 times 3. So 6 minus 6, 6 minus 6, you get 0. Luckily, you get directly 0 below here. Okay, and then the same thing for 7. So 7 minus 2 times 4. So you get minus 1. From 7, you get minus 1. Okay, except, okay, means that the study of the last line seems to imply that 0x, if you rewrite back the second row in terms of the linear algebra just now, it shows us that 0x plus 0y equals to minus 1, which is means that the equation is not valid. Okay, when this happens, this equation have no solution, and we see that the simultaneous equations are inconsistent. Okay, so if you get this type of results, means that this is not this is not true. Okay, we cannot have a linear equation equation like this. Okay, 0 equals to minus 1, so it's not correct. So we can conclude that these simultaneous equations are inconsistent. Okay, so there are no answer, okay, for xy. Okay, so means that this xy, the first equation and the second equation not have the same xy. So it is inconsistent. Okay, other example.
I have a question.
Yeah.
On the previous slide, if we got a luckily 0 y actually, so what about if we don't get 0? How we do a next step?
Okay. This one, example, this one, may other solution, right? Okay, we'll see this one.
Okay, sure.
Okay, okay. Okay, so another example, another algebra equation here. So using the same step, you try to eliminate the component here too. So you have the rules, and then you get 0. Okay, you do the same for the rest of the equation, this algebra. So you get also this one 0, 2 also becomes 0, it's 0, 0. Okay, so imply the same method for the rest of the row. Okay, so this last line, okay, the second row implies that 0x plus 0y is equal to 0. Okay, so this can be correct, 0 equals to 0, correct, but it doesn't help us to get the value of x and y. Okay, but you are now observing a third type of behavior. Another behavior, whenever this happens, we need to introduce what we call free variables. Okay, if we get this type of equation, it is correct, 0 equals to 0. Okay, but we have to introduce these free variables. The first row starts off with a non-zero x. There is now no row which starts off with a non-zero y. Okay, just go directly to the answer. Okay, So for example, means that we have to introduce a variable. So here we just introduce a lambda here, a variable. Okay, so we just said that y is equal to, for example, y equals to lambda. So our free choice or free variable. Then go back to the equation here. Okay, if y equals to lambda, then x equals to minus lambda. Right. So the solution for this linear algebra, these two simultaneous equation, is that x is equals to minus lambda and y equals to lambda. So lambda is any number. So for example, if you get y equals to lambda is 5, so y equals to 5. So x will be minus 5. Okay, check back the verify back in these two equation. So if x is minus 5, y is 5, so you get 0. The same thing for the second row, the second equation. If x equals to minus 5 and y equals to 5, so you get 0. Okay, so means that x and y, the solution for x and y is a free variables. Okay, any number. Okay, any number. So you just introduce one number. Then x will be the opposite signs of y. For example, like this. Okay, it can be also in terms of decimal number or proportion like this. Okay, so you have 1/2. If x is 1/2, so y is the negative, the opposite sign, -/2, and so on the rest. Okay, so the solution is free variables solution. Okay, do I have any other example? Okay, this one we can get all the values. Okay, but this is 3 linear equation, so we have to find x, y, z. Okay, we have to find x, y, z. Okay, so you just write the matrix first. Okay, 1 minus 4 minus 2, and add on also the right hand side of the matrix. So you just write the matrix here. And then the aim again is to eliminate all the numbers below underneath the steps. Okay. So for example, first we need to eliminate this value 2. Okay. So so we figure out the right equation in order to eliminate 2. So the equation is row 2 minus 2 R1. So you need to do the same thing for the rest of the row. Okay, so that's why all these values are have been changed. Okay, you get minus 39, etc. Using the same equation. Means that 1 minus 2 times minus 4. So the same row, the same column. Okay, make sure you do you do the calculation with the same column. Okay, so 1 minus 4. So 1 means that 1 plus 8. So we get 9. Okay, and etc. etc. This one 3 minus 2 times 21. So 2 times 21, 42. So 3 minus 42, you get minus 39, etc. etc. The same thing for the third column. Okay, the third column you have you need to eliminate this value 3. Okay, for the third column. So the same thing, you do R3, the third row, minus 3 R1. So 3 minus 3 times 1. So we get 0, etc. etc. Okay, so we finish the third column. Since we have 3 linear equations, so the method we need to add on, remove another row, another number, okay, unwanted number here. So for the second row is finished, okay, you already get 0 here. But for the third row, you need to also find 0 here, so that we can easily compute the value of this Z. Okay, so the third row, the same, using the same approach. So in order to get this one 14, okay, you need to multiply with the row 2 above here. Okay, we use the second row here. So 14 minus 14/9 R2. R2 is 9. So you get 0 here. So the same thing, the same equation you use for 5 and 6. minus 65 and minus 39, so we get this answer. So the elimination is complete. Okay, okay, so we can now, from this matrix, we can get the solution for x, y, z. So we use first the last line, the last row, okay, the third row, because we already get 0 here, so easily for us. Minus 13.3 z, okay, because the position z here is equal to minus 33, so means that z is equal to 1. Okay, so and then once we get z, we substitute back in the second row and the first row. So if we substitute back z equals to 1 in the second equation, this one, 96 minus 39, so means that we get 6 times with z. Okay, so we can get y equals to minus 5. And finally, substitution of z and y into the first equation gives x3. Okay, so finally, once we get z and y, we can use back the first, this one, to get x equals to 3. So we have solved all the unknowns x, y, z using the Gaussian elimination. Okay. Okay. Okay, last part. Eigenvalues and eigenvectors. Okay, this is the one that you're going to use this method for the course GNC to calculate the control and stability values. Okay, so eigenvalues and eigenvectors. Eigenvalues. Okay, consider the system like the linear algebra equation just now. Okay, just that we have lambda here, an unknown constant, lambda. Okay, so we can rewrite, we can transform these two linear equation into matrix form like this. Okay, 2, 1, 3, 4, x, y, and lambda, a constant, a scalar constant, and x, y also here. Okay, so this one, this matrix can be noted, okay, here A, X, Y, matrix X, lambda, lambda. So lambda is not a matrix, okay? Lambda is a constant, like number 1, number 2, number 3, number 5, etc. So X, Y is the matrix X. Okay, so since that lambda is not a matrix, it is just a scalar number. So actually we cannot write directly like this, okay? Means lambda x. So we need to kind of like change the form of the lambda into a matrix form, okay? So that we can simply add, subtract, multiply, etc. Okay, so remember the identity matrix. Okay, identity matrix. Since multiplying sy by the identity matrix leaves it unaltered, unmodified. Okay, means that if we multiply xy with an identity matrix, it will become xy again since it is identity. So we can just add on an identity matrix here. Okay, it will not change the initial equations, simultaneous equations. Okay, so lambda x, okay, so lambda x may be written as lambda I, the identity matrix, lambda ix. Okay, so if you write this equation and this equation, it's still the same. Okay, because matrix I is identity. Okay, you get the same matrix. Just that we add here because we need to change lambda, since it is scalar, we need to change it into matrix form. So then we can write, which can be written as a lambda minus lambda is equals to 0. We just change the place from the right hand side to the left hand side. So we can factorize x, a minus lambda I, x equals to 0. Okay, so we can write this matrix. This is still a matrix. Okay, then to get first the eigenvalues of the matrix, okay, we need to calculate the determinant of A lambda I just now. This one. We need to calculate to find the determinant of this part. Okay, again, first we have to make sure that the determinant is not zero. Okay, so that the value exists. Okay, so A minus lambda I. Okay, A the matrix A just now minus lambda I is the identity matrix. So you input the lambda here, so you get this new matrix A minus lambda I. So the condition is that this determinant is equal to 0. So you get this form, okay, equals to 0. And it follows that, okay, so if you do like you calculate the determinant just now, okay, 2 minus lambda multiply with 4 minus lambda and minus the 3 times 1, okay, 3, okay, so you get what we call as characteristic equation, okay, characteristic equation here, lambda square minus 6 lambda plus 5 equals to 0. So if you factorize, okay, factorize this equation, you get lambda minus 1 multiply with lambda minus 5. So the answer, the value for lambda in this example is lambda equals to 1 or 5. Okay. These are the values of lambda which cause the system, okay. They are called eigenvalues. So the values of lambda equals to y and lambda equals to 5 is the what we call as eigenvalues. Okay. So we get the values for eigenvalues using these steps. Okay, repeat again. So one, you have the simultaneous linear algebra equation here. So you need to find, okay, this step is just to prove the method. So you can go directly to apply the method. You can go directly and get the A minus lambda I. Okay, and the determinant of this A minus lambda I will give you the characteristic equation. And you solve the characteristic equation, you get the value of lambda 1 or 5. Okay, example, determine the characteristic equation and eigenvalues lambda in the system. Okay, for example, so this one have been written for you directly in terms of matrix. So you have matrix A 3, 1, minus 1, 5. Okay, so the characteristic equation is given by, okay, A minus lambda I just now. So you can just apply the method. Okay, so you calculate the determinant using the determinant calculation. So you get the characteristic equation. So characteristic equation here is lambda square minus 8 lambda plus 16 equals to 0. Okay, so this is the characteristic equation. Now we need to find the eigenvalues, the lambda. Okay. So in order to solve the characteristic equation, we can see that we can have square lambda minus 4. Lambda minus 4 times lambda minus 4 means lambda we only have one solution, which is 4. Okay, so there is one repeated eigenvalue, lambda equals to 4 for this characteristic equation. Okay. Another, the same thing, I think. Kita copy dua kali. Okay. Next. Okay, another example. For 3 times 3 matrix. Okay, here. 3 times 3 matrix. So we need to calculate the determinant. Okay, so we need to calculate the determinant, the same formula, A minus lambda I. Okay, so A, the matrix here, minus lambda I. So remember this diagonal, this diagonal, you need to add on the identity matrix in the diagonal. The rest is 0, the identity matrix. So that's why only this part is minus lambda. Okay. So you do the determinant of this A minus lambda I, calculate, etc., etc. So you get reduced to this characteristic equation, power of 3. Okay, of course, power of 3 because we have 3 times 3 matrix. Okay, we have 3 times 3 matrix. Okay, so we need to solve this characteristic equation. Okay, we just change the positive negative so it will be easier for us. And the characteristic equation is lambda power of 3 plus 2 lambda square minus lambda minus 2 equals to 0. Okay, so factorizing, okay, factorize this equation. Okay, you can get lambda plus 2, lambda plus 1, and lambda minus 1. Okay, we factorize the lambda here. Okay, this third degree equation. So you get lambda minus 2, minus 1, and 1. So the eigenvalues is this. Okay, so the answer is minus 2, minus 1, and 1 for this 3 times 3 matrix. Okay, last one. Eigenvectors. Okay, so eigenvectors basically continuation from eigenvalues. Okay, we have studied the system AX equals to lambda x. Okay, just now, the same matrix just now. Okay, so we need to find the eigenvectors. Okay, so A and X, etc., etc. Okay, so this example is I think the same example just now. Tak ada. This one ke? Example lain. It's okay. Okay, okay. For example, we have calculated the eigenvalues using the step previously. So we get the lambda for this matrix A. The eigenvalues for this matrix A is 1 and 5. Okay, using the same step. Now, okay, consider first the first value of the eigenvalues 1. Okay, we use first number 1 here. I consider lambda is equals to 1. Okay, so the equation just now, A minus lambda I x equals to 0. Okay, the same equation just now. So we replace the lambda with the answer that we already got. Okay, 1. So you have A minus identity I x equals to 0. So just do normally the matrix calculation. So A minus I, you have this one. Okay, because I is a diagonal, okay, identity matrix. So you just A minus I, you get this one. Okay, now this matrix form can be written in terms of simultaneous equation, individual equation. So means that but here the same for both row, we have the same equation. So 3x plus y equals to 0. Okay, 3x plus, remember the multiplication for matrix. So 3x plus y, you get 0. Okay, so means that you only have one equation which is repeated. Okay, so the answer will be, okay, y equals to minus 3x. Okay, y equals to minus 3x. Means that there is an infinite, okay, number, means many solution, number of solutions such as y equals to minus 3x. So for example, if we put x is equals to 1, so using the general solution here, if x equals to 1, so y equals to minus 3. So the same thing, if we put x equals to minus 5, then y will be 15, according to this general equation, and so on and so on. So we have infinite number of solutions, many number of solutions. So generally we will write, we introduce t, the free variable just now, like the free variable just now. So for example, if x equals to t, any number, then automatically y will be equals to minus 3t. So for any number of t. Thus, the eigenvector corresponding to lambda equals to 1 just now eigenvector for eigenvalue 1 is, so vector, we can write it in terms of matrix like this. So the vector x, okay, the solution for this one, the vector x just now, okay, xy, solution x equals to t and y equals to minus 3t. So we can, if you want, we can factorize t, the free variables, so 1 and minus 3. Okay, so in the end, at the end of the eigenvectors, we achieve to the, we can get the solution for the matrix X just now. Okay, note that the eigenvector has been determined to within an arbitrary scalar T. Okay, the free variable is the scalar that we introduced now. Thus, there is an infinity of solution corresponding to lambda 1. Okay, and then we look at the other eigenvalue. We are not finished yet. Okay, we get lambda, the second lambda equals to 5, the second eigenvalue. So the same method, okay, a minus lambda I, x, etc. Okay, so you solve the individual equations, you get these two linear equation. But still, both of these equation are the same. Okay, basically, if you just multiply the first equation with 3, then you get the second equation. Okay, so means that it's actually only one equation. So you solve the equation, you get so the answer for these two linear algebra equation, you get y equals to x for any number of x. So we can write x equals to t. So y will also be equal to t. Okay, so hence, so the eigenvector corresponding to lambda equals to 5 is t vector 1, 1. Okay, so the final solution for the matrix just now, this one, ax equals to lambda x. Final solution, the eigenvectors for that matrix is x1 minus 3 and x1, 1. Okay. Okay, so that's all finished. This is just example how you write matrix in computer programming, MATLAB. So in MATLAB you can write the matrix. For example, matrix A here, the 3 times 3 matrix, 3, 2 minus 1, 2 minus 1, 2, etc., etc. Like this. Okay, you just put the first column at the first row, 3, 2 minus 1 with comma, 3, 2 minus 1, and then the semicolon here, okay, to differentiate the first row and the second row. Okay, this is how you write matrix in MATLAB. Okay, so for example, this one 4, 10, and 5 can also write like this. Okay, so since it only have one column, so you can write them like this. Okay, so the comma used to separate the entries and the semicolons used to separate the different row. And then you can use directly the formula already included in the MATLAB, inverse A, to calculate inverse A. And then you can use this definition just now to calculate, to solve the linear algebra equation, okay, to calculate the value of x, the xyz just now. So you get the answer for xyz using the computer programming 3 minus 2 and 1. Okay, so I think I have finished. Okay, I finished the slide. Okay, so I have put up this one matrix tutorial here. Okay, so you can if you have time, this is just for your own self. I mean, I'm not going to you don't need to submit or anything. Okay, this is just for you. Okay, you can look at the example exercise if you want to practice. And I already put all the solutions here. So that is more on the calculation part. So you just need to practice to familiarize with all the procedure steps just now, determinants, how to calculate the determinants, how to calculate to use the determinants to solve the Cramer's rule, the inverse matrix. So I think it's not too hard. It's just that you need to get to use to it, okay? To get to use all the calculation steps, Gaussian elimination, eigenvalues, eigenvectors, and that's it. Okay, so there are all these exercise tutorials that you can use to practice. Okay. Okay, I think I finish here. Okay. Any questions? Anything? So you can download the slide just now. Okay, and the tutorial here in 12. Okay. Okay. Any question? No questions?